Hi everyone, this is Chen Chen. I'm a system architect from 4Paradigm. Today I will share our work optimizing in-memory database engine for AI-powered online decision computation using persistent memory. This is a joint work between 4Paradigm, National University of Singapore, and Intel. Over the past decades, artificial intelligence has increasingly attracted a lot of attention from both academic and industry. Online decision augmentation has been widely used in many applications, such as real-time fraud detection, personalized recommendation, production forecast, and so on. 4Paradigm is an emerging pioneer who provide OLDA solutions to more than 8,000 customers during the past 5 years. In this study, we first use a real-world fraud detection system as an example. It has already been deployed in a top bank in China. We describe the entire data processing to summarize the characteristics of the OLDA applications. As shown in the figure, when a user swipes the credit card through a POS machine, it will generate a new original recall. When receiving the request, the OLDA system first inserts the new transaction into an in-memory database, then immediately extract features based on the user's historical behavior. Those features are fed into a pre-trained machine learning model that score and predict the probability of the fraud. Both the user's behavior as well as the fraud result will be used as a feedback for offline training system. In the entire OLDA cycle, the online inference process has a strict time constraint, which is also the main focus of this paper. After profiling, we have identified that real-time feature extraction is a performance bottleneck. Feature extraction can be recognized as obtaining the hidden information in the raw data, and it has the following characteristics. Firstly, most of the real-time features cannot be pre-extracted until the new recall is received. Secondly, most real-time features are time-related and required token to be computed over multiple time windows. Based on our experience, the more time windows are involved, the more accurate the prediction will be. Lastly, in practice, our OLDA system extracts thousands of the real-time features for each prediction, which dominates the overall response time. The feature extraction is quite different from the traditional database workload. We have evaluated such workload over a series of in-memory databases. Here, we list the two state-of-the-art commercial in-memory databases that we will not name publicly. The latency of both DBX and DBY are more than 100 milliseconds when the number of the time window larger than 3. In practice, our fraud detection system requires to finish such operations over more than 10 time windows within 100 milliseconds. It is obvious that both of them cannot meet the requirement. Motivated by above observations, we propose feature engineering database. FEDB is an in-memory database engine specifically designed to support online feature extraction. It consists of two parts, FEQL and a storage engine. FEQL is a circle-like language which not only supports most of the standard SQL, but also introduces some new syntax. For instance, FEQL can define multiple time windows in a single query so that the execution of such top-end query can be optimized. In the storage layer, we adapt a DRAM-based double-layered Skiplist as an index. The time windowed query can be performed by searching the first layer Skiplist for the specific key, followed by scanning the second layer Skiplist for the given time window to locate the raw data. We compared our FEDB with previous commercial databases. FEDB constantly outperforms both databases when the number of time windows increase from 1 to 8. More importantly, the results show that the more time windows are involved, the bigger the performance advantage FEDB gains. After deploying the fraud detection system to the bank, we find the DRAM-based FEDB has the following limitations. First, the fraud detection system occupied around 10 terabytes to store data in memory. Both the huge memory consumption and the limited size of the DRAM capacity per server significantly raise the total cost. Second, the traditional in-memory database have to sync the data from volatile DRAM to slow HDD or SSD. The tail latency can be too high to meet the strict time constraint when workload is heavy. Lastly, the traditional in-memory database take a few hours to load data from the backup system to DRAM after failure. Such long recovery time affects the system availability. Compared with DRAM, Intel Optane persistent memory, which is also called PMem, has much larger capacity. It is also byte addressable and non-volatile. PMem gives us a good opportunity to address above limitations, and it can be worked in the two modes, memory mode and FDRAM mode. In memory mode, PMem is working as a system memory, while the FDRAM mode provides a way to directly access PMem as a byte addressable persistent device. In this work, we choose FDRAM mode, and we remove the traditional log and the snapshot flash process. Most of the PMem data structure applying logging or copy on write to guarantee the consistency. Those approaches are not efficient. As we know, CAS is an atomic instruction using in multi-threading to achieve synchronization. However, the traditional CAS may cause an inconsistency issue when applying on PMem. Here's an example. As shown in the figure, we assume that thread 1 received a new credit card record T1. We use a CAS to add T1 to the last layer of the Skiplist. Since those data is still in volatile CPU cache, we call a CPU cache flush command, such as cell flush or cell WB, to flush T1 back to PMem. During this process, thread 2 extract feature F1 based on T1. For instance, F1 stands for the amount difference between the new record and the last record. We also need to call CPU flush command to persistent F1. Since CAS and CPU flush command are totally independent, the power failure may happen between the two flush commands. After recovery, F1 still can be accessed, but T1 lost. Then the system is inconsistent. Thus, we propose persistent compare and swap mechanism. We first solve CAS correctness issue by using a flush on read strategy, which means we flush the data before read to guarantee that all the data we read are persistent. Meanwhile, to avoid unnecessary flush on clean data, we leverage a small pointer whose lower 4 bits are used to indicate whether the data is clean or not. We propose a PMem-based persistent Skiplist and redesign the process of insert, delay, and the search in the persistent Skiplist by using PCAS. To further reduce the amount of PMem write, we only store the last layer of the Skiplist and the data on PMem. Thus, we developed a recovery process to rebuild the whole Skiplist when system failure happens. In the experiment part, we use our real-time fraud detection workflow to evaluate both DRAM-based, PMem-based FEDB, as well as two state-of-the-art commercial in-memory databases in DRAM. The data size of the workload is shown in the upper table. We deployed 3 replica, so the total size of the memory is around 10 terabytes. We first compare the top 50 latency among all the databases. The results show that FEDB can achieve up to 37 times to 610 times faster than the state-of-the-art commercial database. Then we use DRAM-based FEDB as a baseline to compare the performance of different PMem-based FEDB. The result shows that the PMem-based FEDB can shorten the tail latency, reduce the recovery time, and save the total cost of the ownership significantly. We conclude the paper. In summary, in this paper, we first characterize real-time OLDA. We propose FEDB and then use Intel PMem to solve its limitation. We evaluate the real-world workload on databases and show the promising result. Now, we already open source both the PMem data structure as well as our FEDB, now renamed as OpenMLDB on Git. For Paradigm and Intel also built a technique community called MemArk, focusing on modern memory and storage architecture. We also listing a PMem version Kafka here. We are welcome to download and try. Thank you.